Welcome everyone. Please confirm you can hear me. Um, okay, so if you cannot talk at the moment, you can just react. I want to be sure that you can hear me. Though we'll be starting by 10 a.m. It's on dot, but I just want to be sure that I am audible and you all can hear me before we start. All right, thank you. I think I've seen a thumbs up. Thank you very much. Welcome everyone. So we'll still wait for 1 more minute before we start because we don't want to take much of our time for today's section. So we'll just go straight to the business. All right, thank you for joining once again. So we'll just give grace of 3 minutes to see who else wants to join before we start. Um, Thank you very much. Um, Good luck, Obo. Thank you. Sorry. All right, all right. Good morning, good afternoon, good evening for wherever you are joining us, and welcome to Harvest Geo Solutions first webinar series. We are excited to have you join us today as we discuss an important topic. titled Increasing Reserves Using Foresee Analysis in Appraisal and Development. My name is Wura Olanureni, and I will be your host for this session. Today, I'm honored to be joined by three distinguished speakers. Olaitan Kobiowu, who will be guiding us through FORT evaluation. We also have Prosper Uzoma, who will discuss the impacts of FORT on reserves. We talk more on league points and share one or two case studies with us. And also our esteemed consultant, Mr. Titus Murray from Southern Island Structural Geology, who will be also providing his expert insights. And briefly, I would just be reading the profile of our speakers for today. Okay, so the first speaker for today's section is Olaitan Kobiowu. Olaitan has a BSc in Geology from the University of Ilorin, MSc in Petroleum Geoscience, Uniport, and she's also vast in data analysis she had this data analysis certification from Utiva School. She's a geoscientist, a subsurface data analyst at Harvest Geosolutions Limited. She is a member of NAPE and WIGE. Um, Olaiton is an event planner and she's into catering. She also has interest in business development. For her leadership roles, Olaiton is the lead for digital and communications for WIGE, and she's also the events and welfare manager for NAPI YP. She's interested in children. She loves children. She loves reading, traveling, cooking, and also networking. With a show of hands, can we please appreciate our light, Uncle Bio? All right. Thank you. Thank you. Please let's encourage our, yeah, thank you very much. All right. So the second speaker for today's session is Prosper Uzoma. Okay, so Prosper is a geoscientist at Harvest Geosolutions. Um, he has his MSc in Petroleum Geoscience from Obafemi Awolowo University. Prosper's skill set entails force analysis, seismic data processing, and interpretation techniques. He's also a member of NAPE and also a member of NAPE Rapporteur Community, and is in the technical team for NAPE YP. Prosper is interested in youth empowerment, team or individual sports. He loves reading, music, and he also loves traveling. Thank you as you appreciate our second speaker, Prosper Uzoma. All right, and moving on to the third speaker for today's session in person of Titus Murray. Titus Murray is a director at Southern Island Structural Geology, is the president of the Petroleum Exploration Society of Australia. Titus' specialties are in foresee analysis, structural restoration, fracture prediction, tectonic integration, and numerical structural geology. He is also a supervisor to various PhD students whose research findings are a result are being used to develop the Fortreef software. And the Fortreef software is actually a proprietary software that we use at Harvest Geosolutions for our fossil analysis. Without further ado, let's go straight into business. Over to you, Olaiton. Thank you.
All right, thank you, Wura. Please confirm you can hear me.
Yes, we can hear you, Olaiton.
Okay, thank you very much. Good morning, good afternoon, good evening to everyone from wherever you're joining from. Thank you so much for joining us on this webinar this moment. And as Wura has introduced us, three of us would be facilitating this session just for few minutes, and then we'll take questions. We already have some questions while people were doing their registration. So this is a webinar for us to understand how FORT is essential in appraisal and development stage. I believe that we all know like the oil and gas assets, and we know the several stages involved. And for over the years, like we've worked on the exploration aspect, and now like we're moving on into the appraisal and development aspect. So the topic is still in the deal, right? So just we'll start with just basics, like basics that I believe that most people here, like we all know, especially geologists or even basic geophysicists. So it's the fault story, right? We all know how fault is being formed. We all know that when fault is formed, we have the hanging wall, we have the foot wall, and from the diagram, this diagram just encapsulates like everything that you need to know about fault, right? You can see the several blocks, you can see the angle of dip, you can see the strike, you can see the various types of faults that we have, the normal faults in the reverse faults, and also the strike slip faults in sinister or dextral faults, right? And just the common thing that we work with in under delta, or the common type of faults that we see, especially in maybe offshore, onshore, before we go to the deep, ultra deep offshore, right? It's just a normal fault. Now we know that when we get into the ultra deep offshore, we start seeing some thrust tools like that. Okay, so what we do at Avex Geo Solutions basically is when we get this data, this fault data from clients, we don't just go ahead to use that fault just like that. We have to do some evaluation, right? And it's just like for every one of us, when we try to relate this to our personal lives, like it's just when you want to do an evaluation, like when you apply for a particular job, right? The employer has to do some evaluation for you, for them to know that you are right and fit for the job. So that is what we do with default polygons that are being provided to us from the clients or by the clients. So what we do basically is we make or we evaluate this fault for them to be fit for analysis. And what do we do in evaluation of the faults? We look at fault geometry. So now when we talk about fault geometry, basically we're looking at the throw and the length of fault. And because what we do at Avex, like we tend to follow, like it's like standing on the shoulders of of giants, people that worked in the past, people that have done these things. So we use this particular theory by Schultz and Forsen, and this theory is just governed by the fault through length ratio. And basically what these guys did is they did a study of various like faults from different places, and then they characterize them into three different categories. So we have the seismic scale faults, we have the regional faults, and we also have the outcrop scaled faults. So the idea is that for a fault of a particular length, you should expect a particular range of throws. And when I think about this thing, it's just like someone like me, if you have seen me before physically, I'm quite short. So the kind of door that I'm able to pass through is different from maybe someone that is so tall, like a giant, like we pass through. So like our heights are different. So therefore, our throws should be different, right? So that's the way the like fault is also. When we talk about fault, when you see a fault of about 20,000 meters in length, and you are seeing like let's say 20 feet of throw, like you start like raising eyebrow and be like, this there's something wrong. I remember a particular project that we worked on, and these faults are like I think almost 5,000 meters in length, and the throw was about 17 feet. We had to take that data back to the clients, and they actually saw the mistake that they made during the interpretation, right? So this is basically like how we just study the faults using the fault geometry, the fault length, and the fault ratio. And for this particular one, we actually did a study related to this, and we presented this paper last year in NAPE conference, where we took several papers, like I think over 30 to 40 papers, and we digitized the fault manually by ourselves using our software, and we put the faults on on the table. So it just shows how these faults are characterized based on the regional ones, the outcrop, and also the seismic scaled fault. So after doing this, another thing that we notice is sometimes when seismic interpreters, when they interpret and when they map these faults, they tend to map some faults that they are actually like more than one. They map them as one fault. So we look at the displacement and throw, which helps us in splitting the fault. And I would show examples of different faults that we have like done in the past, just few one or two ones that we have done in the past. And this particular one is just based is after Barnett 1987. And what he says basically is that displacement is zero at the tip of at the four tips, and it increases to a maximum near the center of the fault surface. So when you have like your maximum throw is supposed to be at the center of your fault. So now let's just take this scenario. You know this rope jumping ropes, these jumping ropes games, when you have one person jumping the rope, then the maximum like the maximum height of the person will be at the center of that rope. But when you have two people jumping that rope, one two, then you see like you have the maximum throws like just at the center and another one, so you have like two loops like just what we have in this particular in the second diagram. So for this first one now, where you have the foot or the hanging wall, and then you can see the throw line. This is just showing a single fault. But in the second place where you have two maximum throws, you know you are working with two faults. So what we do here is we split the fault and then we name it maybe fault 1A and then fault 1B. So after doing this, let me just show you like how our displacement profiles is. So this is like a tip. This is a public. Just took this map from a paper. I think we worked on this in 2023 for a technical presentation at SNAPI. So when you can look at this map and then the fourth west, this is how the displacement profile looks like. So what are displacement profiles? So basically it shows us the footwall, the hang at the hanging wall, and it also shows us the theoretical. So theoretical basically is how the fault is meant to look like, right? Based on the throw of the fault, based on the end throw, the left throw, this is how this fault is supposed to look like. But based on what clients or based on what you are provided, this is what you have. So you have the observed, and you can also see the if plot. So another thing that we do is we try to slim fit the eve, and I would explain why we do that. So you can see how Fort West is looking like, and then let's look at Fort East. Fort East is looking like that. So we're not just going to use we're not going to use a fort like this. We need to, we need to adjust it to look like the theoretical, at least to remove the spikes. And most times when we do that, we work on we work on the hanging wall, right? We work on the angle because we know that the hanging wall is the wall that has moved. It has moved. So therefore changes must have been done or things must have happened in the subsurface. So now let's look at this second example. This second example is from one of the work that we have done. And if you look at the displacement profile, so we have 46. Remember what we said at the beginning when we after Barnett, where we have to split faults that have maximum throws, like where you can see like two spikes or something like that. So for this particular example now, so first is you can see the displacement profile, the foot wall and the hanging wall, and you can see how the throw is looking like. So for this now we have to split into two, and we have to split into 6.1 and 6.2. Look at the separation in the eve. So most times, like when we put this in the software, you see that the eve is looking, maybe you have like 20 degrees or 30 degrees or 40 degrees, and we know that normal fault in Nigeria Delta, normal fault is 65 degrees. Would explain why that is like that. So we remove the spikes from the hanging wall because we know that it is commonly poorly imaged as it has moved, and then we now segment the fault into different geometric segments. So now let's look at the second diagram, which is the 6.1. So this is a segment of that particular fault. This is of fault 6, which is 6.1. You can see the theoretical and the observed. We've tried to edit or evaluate the observed to look like the theoretical. And you can see that the if plot is now looking slimmer, right? At this point now, the angle is around 65. Sometimes when we have 64.8, 64.9, we just let that be. Then you can see the second one, the 6.2. Also, we have adjusted the eve so that it could be in the 65-degree range. So now let me explain why we have the 65-degree. So remember the Anderson theory of fault, right? And when we talk about the Anderson theory of fault, there are some three major stresses that we must not forget, or we must always mention. We have the sigma 1, 2, and 3. Sigma 1 is the maximum principal stress, and sigma 2 is the intermediate principal stress axis. Sigma 3 is the minimum principal stress axis. So we can look at how normal faulting, how the stress regime of normal faulting is, looking at the faults in red, the joints in green, and the stylolites in blue, right? So one thing that we just need to know, and why we have normal faults to be at angle of 65, is because normal faults will normally form at an angle of 65-degree along the angle of along the maximum principal stress, right? That's how normal fault is being formed, and that is why we have to make sure that when we are interpreting the fault, evaluating the fault, we should have 65-degree or within the range of 55 to 75 degrees, as the case may be. All right, so I will just hand over to Prosper to take us on how this impacts our reserves and how we can actually use port sale in appraisal and development. Thank you very much.
All right, great, Olaitan. That was a really great one. That was a good one. Thank you so much for um, like the Bible will put it, that John the Baptist was the forerunner of Jesus. So you've essentially cleared the way, or made the path straight for me. Yeah. So very quickly, we'll be using what Olaitan just spoke about to look at how all of that could impact on our reserves. So stick with us and let's look at how all this stuff we've been hearing, how does it impact on reserves? So now we'll take you back to our volumetrics, right? And we'll take you back to our volumetrics. Next slide. And we see that in calculating or in carrying out volumetrics, a key parameter is our gross rock volume, if we still remember our STOIP calculation. Okay, and we know that our gross rock volume entails, we're looking at both area and height in terms of hydrocarbon pool. All right, so now let's consider this faulted structure. So we're taking it back to the basics, right? So that is quite clear and everybody is on the same page, so that we're not losing anyone. So we have a faulted structure. Ideally, when we are mapping our horizon or picking our horizons, mapping our faults, and we have a fault that, would I call it an obese fault, if that's the way I'll put it. So we have a fault that has a sort of heave as large as this, but then because from leading from what Olaiton has told us, we know that ideally normal faults deform, or the rock deforms along the maximum principal stress and at an angle of 65 degrees. Therefore, our faults have to be on a diet. You see what I did there? I called the faults obese at first. Now we have to put them on a diet. So how do we go about doing that? Next slide. So what we see is that first, even before looking at putting our faults on a diet, we should be able to first of all identify what our hanging wall is and our footwall blocks, or what our hanging wall and footwall blocks are. So we do that, we put our fault stick to our faults. So now we know our hanging wall, we know our footwall, basic stuff. Now we have an area where we have our hydrocarbon pool. indicated by the red polygon. And now we want to calculate our area. So how do we do this? From some of the basic stuff that we were taught, if some of us do remember, manually, even before going into software such as Petrel and clicking buttons and all of that. But manually, we draw or we create a grid, so to say. So we have our scale, which is 2 kilometers, and then we have these boxes, which means each side of the box is equivalent to 2 kilometers. So essentially, we identify how many full boxes we have within the area where we have our hydrocarbon pool. And then for boxes that are not up to 1, that is not up to a full box, we identify or we assign an appropriate fraction of what we think defines the area the pool or the hydrocarbon pool covers for that box. So now we see that, this makes it quite basic and straightforward, and we sum up all of this, our 1s, 1/3, 1/2, 3/4s, and we have 27.1. So we remember we have a scale, which means that each side of one box is 2 kilometers, which is 2,000 meters. And that means the area of one box would be 4 million square meters, right? Again, simple maths. And if that's the case, we multiply that with 27.1, which means the area of where we have a hydrocarbon pool will be 108.4 square kilometers, or 108,400,000 square meters. Now, this is where we have an obese fault. Okay. Now, watch out to see what the impact of putting your foot on a diet will be. Just watch what we're going to see in subsequent slides. So in the next slide, now we've put our thoughts on a diet based on what we know about geology, normal faults, having deep angles of 65 degrees and all of that. So immediately you see that the area covered by which you have, or the area which you have your hydrocarbon pool gets bigger. Okay, when you put your force on a diet. And then we follow the same due process by calculating our area, same grid, all of that. And when we do this, what we would have, I think there's a lag to the slides. So what we would have, same process with the grid. So remember we had 27.1 previously, now we have 33.1. We multiply that with the same area of one box, which is 4 million square meters. Okay. And now we have 132.4 square kilometers, or 132,400,000 square meters. For the obese fault, just to remind us, we had the area of our hydrocarbon pool was 108,400,000 square meters. But when we put our foot on a diet, we have 132,400,000 square meters. See that this is a huge impact on volumetrics, because these two values would give you entirely different results in terms of your volumetrics. So by the time you calculate your STOIP, and then you calculate your reserves, your recovery factor, you see that these two values will hugely impact on what you get at the end of the day with your reserves. Very straightforward, and this buttresses the importance of we putting our thoughts on a diet and ensuring that they are have that deep angle of 65 degrees, at least for normal foot. Now, take it a bit step further in terms of looking at leak points and fluid cutters. So we've looked at area and how following the right or doing the right due process in terms of your fault evaluation can really help you or impact your reserves. So in terms of leak points and fluid cutters, now let's consider scenario 1. We have a normal fault, we have sand and shale units. Now, we have hydrocarbon accumulation on the hanging wall of the sun. So what we observe is that this sand is juxtaposed with the shale. So in terms of fault seal, evaluating your faults, we are looking at juxtaposition in terms of technique, juxtaposition, SGR, and all of that. So this is what essentially what everyone wants. So you want your sands juxtaposed with your shale so that you could have this large pool of hydrocarbon. Okay. But then in scenario 2, where we have essentially the same, maybe a little bit different in terms of how the sequence goes on the hanging wall. But now we have a sand to sand juxtaposition. And what this creates is a possible leak point, or it's a leak point between the sand, which has the hydrocarbon accumulation, and the sand on the footwall. And what we would see happening is that because this is a leak point, you would essentially have hydrocarbon migrate from the hanging wall to the footwall. And you would not know this essentially unless you carry out fault seal. Because this then gives us a good idea of what's happening both across our faults and also within our reservoirs. Because we've seen that, and any of these scenarios again is possible in the subsurface, where you have your sands juxtaposed with shale and you are all good, or then you could have your sands juxtaposed with sands, and then you have, I think there's a lag, then you should have hydrocarbon pool on the footwall of the fault. Next slide. So there's a leak point, there's a migration showing migration of the hydrocarbon across the fault. That's the hydrocarbon pool. And you have your water and you see different fluid contacts. But then we'll present a third scenario to you. A third scenario which is possible. Now, you have a sand on the hanging wall with hydrocarbon accumulation, hydrocarbon pool. And we see a sand to sand juxtaposition as well with that sand on the footwall of the fault. So what happens is the same sort of procedure or observation which we observe with scenario 2. We see again leak point between both sands and migration too of hydrocarbon across the sand. And we have our hydrocarbon pool. But what you observe is that the sand on the hanging wall is again the fluid contact, even though controlled by the spill point, right? You have a leak point across the fault and hydrocarbon accumulation on the footwall of the fault. We see that because of this, the fluid contact that is observed in both sands, both at the hanging wall and the footwall, would be the same. So in that case, you might, or if in a case where you drill 2 wells, rather, you'd see the same fluid contacts in both sands. But then you might not need to drill 2 wells. You might just need to drill 1 well on the footwall. And with that, you are able to produce the polygon, the area which we've identified with the purple polygon. You're able to produce both what is on the footwall and the area which we've identified with the purple polygon. However, you might not be able to get to this attic. But then you will need to, if you want to produce what you have in the attic, you will then need to drill another well on the hanging wall. So we see that, again, this just buttresses the fact that we conducting fault analysis, we've identified 3 scenarios which are possibilities in the subsurface. They are all possible. It's possible to have any of these happening in the subsurface, but you won't get this understanding until you carry out fault analysis to understand what the possible juxtaposing scenarios that exist. What are the juxtaposing scenarios? What is your share guard ratio telling you? You won't know what scenario is existent in your asset or in your field until you carry out forcing analysis to get this insight or knowledge. So I hope that makes sense to somebody. And moving on, would just look quickly so that we can get onto the questions and answer section. So we'll just look quickly at a case study. I know it is case studies, but it's just one case study. So um, so we've tried to sketch out this just to show us what we did in terms of this project. This was one of the projects that we did for an operator, and the case here was that we had a major structure building fault, which is fault A, separating what is a discovery and then a prospect on the footwall of fault A. So the goal, again, the operator planned to drill an appraisal and development where they wanted to improve their exploration portfolio, increase reserves, which is what everyone wants to do, and understand if there's communication between the hanging wall and footwall blocks of Fort A. So looking at or taking a bit from the scenarios that we've shown, so we discovered again the discovery and then a dry well on the footwall of Fort C. So our interest essentially was this prospect here between the footwall of Fort A and the hanging wall of Fort B. So we looked at juxtaposition scenarios, some of which we might not be able to share on this webinar. Looked at what SGR was showing, and we observed that for this prospect, that for a number of reservoirs, there's a possibility, a high chance of hydrocarbon being trapped within this prospect. And we did that because we are dealing with subsurface data, right? There are a lot of uncertainties. By applying the fault sheet techniques, juxtaposition, and edge, like I've mentioned, with a stochastic simulation approach, which is a Monte Carlo simulation approach running 10,000 iterations. So we looked at the faults, looked at stratigraphy. Of course, your stratigraphy helps you to know what units are juxtaposed against each other. And we observed that there is a high chance of this fault acting as a good seal or a good trap, right? And this information was very vital because this prospect was matured, has been drilled and matured as a discovery. But the thing is, again, you will not know all of this or get these insights except you carry out force analysis or you conduct force analysis. So with this, with the insights which we provided in this case study, we helped the operators to increase their reserves and their exploration portfolio. So I think perhaps I've spoken a lot. I'll leave it at this. We'll take some questions. I'll hand over to Rola at this point. And if there are questions, yeah, I think this is the point, Wura. Over to you. Thank you so much for listening. Thank you.
All right. Thank you, Prosper, for that insightful presentation. Now, we'd love to hear from you. At this time, we are opening up the floor to questions from our audience. So if you have any questions, please signify by raising up your hand or dropping the question in the chat box, and we will address them shortly. While we are still gathering your questions, we have received some questions from those who registered, and I'll be reading a few of them for our speakers to address. Okay. So I think the first question here says, how can one validate the Fosse analysis model given the limited wells on both sides of a fault structure? Um, all right, so Prosper, can you please take that, address that question for us? Thank you.
Okay. So how can one validate the FSA model, force analysis model, given the limited wells on both sides of a fault structure? So, yeah, that's an interesting question. One that I think we get this question quite often. So the thing is, to keep it quite basic, so to say, it's about going to or going back to first principles of geology, right? So if you have a well on one side of the fault, say the hanging wall, or maybe the photo, let's say the photo. The question is, was the fault propagated? Is it a syn depositional propagation, or was it propagated after deposition of your stratigraphic units? Because if that's the case, if you had your fault propagation after sedimentary deposition of your so essentially what that means is that you have the same stratigraphic sequence on either side of the fault, right? Um, which is uh, following what we know about sequence stratigraphic principles. But if the fault, if it's a syn depositional sort of propagation in terms of the formation of your fault, then we would start considering things like growth on the fault, which we would need to integrate uh, into our hanging wall stratigraphic sequences, because we know that the growth would be seen, or the effect of the growth would be on the hanging wall stratigraphic sequences. So it's just about going back to first principles of geology, stratigraphic sequence, or sequence stratigraphy rather. Was the fault formed after stratigraphic deposition of stratigraphic units? If that's the case, you will have the same stratigraphic units on either side of the fault. If it's not the case, or is the case that the fault is a syn depositional propagation, then you need to integrate possibility of growth on the hanging wall stratigraphic sequences. So I don't know if that helps. Yeah.
All right, thank you very much, Prosper. The beginning of the call, I mentioned that we'll be having our consultant with us, and he's currently on the call. Mr. Murray, I don't know if you have any addition to the answer that Prosper provided for that question.
No, I think Prosper gave very good summary of that. I guess the interesting thing is with the growth faults, one of the things we've seen is that if we've got a growth fault, we end up with different sediments in the hang wall, and this can often be a different exploration trap. So we're sitting there saying that, we know that we've got something different in the hang wall. Have we got effectively a stratigraphically separate sand in the hang wall? And from the work that we've been doing in the Niger Delta and other deltas like it, this seems to be a really important feature.
All right.
Yeah.
All right. Thank you very much, Mr. Murray. All right. So the second question says, what are the applications of machine learning in fossil analysis? Olaiton, do you want to quickly address that for us? Thank you.
Can you hear me? All right, thank you. Thank you for that question. Were applications of machine learning in fault analysis? Yeah, it's actually quite broad because machine learning is even applied to everything nowadays. Like everything, you can even apply machine learning to if you want your baby to stop crying. I remember one particular Wige event in which Mr. Michael Aku he made that presentation about how he was able to develop like something through machine learning to stop his baby from crying every time, right? Okay, so but in terms of we using machine learning in Havex for fault analysis, it's just basically the software that we use, right? And the fact that we have been able to develop the software to do a stochastic simulation, not just a regular deterministic, is through machine learning. So it's very it makes work easier, it makes work better, it also makes it more efficient and effective, right? So the use of machine learning, it cannot, it's just very important. Yeah.
Thank you very much, Olaito. Mr. Murray, do you have any addition to that before we take questions from the audience?
Yeah, look, I guess the main one with the machine learning is that we're playing around with all sorts of ideas about stratigraphy, but any machine learning has to be based on a logic. And one of the things we try and do that Prosper was going through was showing what's the logic of the trap. And I think where we need to go with the machine learning is to define the logic first and then see how we can use the machine learning to better understand uncertainties rather than it doesn't solve the fault seal problem, but it helps us better understand what the seal facies are, for instance. That helps.
All right. Thank you very much, Mr. Murray. I think we have one person answer. AGK is a okay, so you can unmute yourself now to speak. AGK. Oh, you can't. Okay, let me try to. I think you can unmute now. Try to unmute so that you can speak. Hello, AGK, can you hear me? All right, so if you cannot speak at the moment, you can drop the question in the chat box, but you can unmute if you can hear me. All right, so while AGK is still trying to come on board, we have one question in the chat box, and that question is from Adekunle Osundina. He's asking, how can you use seismic inversion in fossil analysis using an inversion result which gives information on the lithology? How can you use seismic inversion in fossil analysis using an inversion result which gives information of the lithology? Mr. Murray, you can go ahead to answer the question. Thank you.
So I've literally been doing a project last week where we've been doing this. And look, there are a couple of things to be really careful. The seismic inversions are getting really good. I was using an inversion that's been done by in Australia here. One of the biggest hassles we've got with inversions is they tend to be biased on inverting for sand properties, and often it's really hard to get the shale properties. So it's super important when you're commissioning the inversion to make sure that you're inverting equally for the shale, because as Prosper showed in that little mental models on the seal, the cross-fault seal, finding the primary juxtaposition is the really key thing to this. And the hassle we've had in the project I've been doing most recently is we had a pretty good idea about what was in the footwall of the fault, but because the hang wall was close to the edge of the seismic volume, it looked really sandy, and we don't think it is. So you have to be really careful to sit there and think about what it is. And it goes back to that initial question we had about how do you model when you've only got one side of the fault? So the inversion can really help with that, giving us an idea about what's on both sides of the fault. You have to be super careful that you also invert for shale properties, and in particular look for shales that are coherent and connected. Does that give an answer? Does that help?
Yeah. But can you unmute it? Can you unmute? Is it possible for us to unmute someone?
All right, all right. Let me try to. I think AGK now has permission. You can try to unmute again.
Or maybe you can just type your question.
Or yes. And if you are still having difficulty, you can type in your question. Okay, so someone is asking, okay, Uchechukwu Wale is saying, can we get the recording after the meeting? Yes, we would. So this webinar session will be available on our YouTube channel. We have a YouTube channel where you can watch the recording after today's section. All right, so does anyone else have questions? Please drop in your question in the chat box if you cannot speak. I mean, we have the privilege of our consultant today.
We've got the question, what specific steps, methodologies can be applied in the fault seal analysis for uncertainty quantification? And I guess, right, and then there's another one coming about juxtaposition analysis. Okay, I'll just answer the GK's question first. So we haven't gone through it in all of these slides, but when the software allows us to define the stratigraphy as a set of distributions and also the fault as a set of distributions. And so this is what Prosper was saying in his section and talk was we do a Monte Carlo simulation of the fault plane, and that's how we model the uncertainty. And in the uncertainty analysis, we are tracking the juxtapositions windows and the shell gouge ratio to check which element is the key, most important element of the fault.
All right, thank you very much, Mr. Murray. I think the second question, sorry, my network is trying to be funny. I didn't see the first question. So the second question says, in your juxtaposition analysis, that is sand to sand, what is the effect of smearing and mineral components along the fault plane and leakage?
You want me to take that?
Oh,
yeah, sure,
Prosper, go ahead.
Yeah, I'll just comment on that. If Mr. Murray has something to add, then can. So, in your juxtaposition analysis, example, your sand to sand, what is the effect of smearing a mineral component along the fault plane and leakage? Okay. Yeah, fantastic. So most school of thoughts would say that when you have your sand to sand juxtaposition, then you should go ahead to look at the membrane seal, right? And one of the algorithms or the most widely used membrane seal algorithm, which is your shear guard ratio, which looks at the content, the shaly material within the fault zone, phyllosilicate materials within the fault zone, right? So the idea is that the greater the amount or the content of phyllosilicate materials or shaly materials which you have within your fault zone, the greater the chance of sealing. Okay. There is a widely used rule of thumb which says that SGR of 0.2 and greater than or equals to 0.2, to some extent would start supporting the fault sealage or fault sealing rather. So if you have greater amount of shaly material within your fault zone, that would support greater possibility of your fault sealing, right? So, but if you have or little amount of phyllosilicate materials or shielding materials within your fault zone, then a greater chance of fault leakage. I don't know if that helps. Mr. Murray, if you want to add to that.
Yeah, sure. So that's the algorithm that's commonly used. I think there was a question somewhere in there. One of the things we found that this varies a lot, and it's super important to actually do calibration studies. So this is where old wells are particularly useful. So if you've got in your exploration block dry wells that have been drilled with valid structures, we go through and check how well they seal. And the other thing is known hydrocarbon accumulations with reasonably well-defined fluid contacts. Can we predict using the modeling using the juxtaposition and shale gouge ratio modeling, how well they predict? Our experience from around the world is that whilst the shale gouge ratio gets used a lot, it hasn't been as good a predictor of fluid contacts as juxtaposition.
Yeah.
So in general, juxtaposition will give you a smaller column, but it'll give you a much higher degree of certainty. And so this is all the question you want to ask yourself. Do I want a very optimistic solution, or do I want something that I'm happy is going to be a successful solution? And this gets tied into the uncertainty analysis we talked about before, that we're Monte Carloing the shale gouge ratio algorithm as well as everything else.
All right, thank you very much. And still on the shale gouge ratio, someone is asking on SGR, what exactly is the acceptable range of values for the SGR to be certain of a good seal on the fault, assuming a sand-to-sand juxtaposition?
Do you want to take that one again, Prosper? Because that's really similar to.
Yeah, that's quite.
Yeah.
Yeah. So, I think I highlighted a little bit about that when I was answering the last question. So, uh, based on works that have been done around the world on SGR, where you are not muted. So, based on works that have been done around the world, um, in terms of SGR, there's a rule of thumb that says that SGR greater than or equals to 0.2 would suggest port sealing to some extent. So that's the rule of thumb that sort of guides what we know about SGR in terms of fault sealing or fault leakage. But obviously, you want to have SGR greater than that to have more confidence, so to say, right? The greater the SGR you have, the more confidence you would get, right, in terms of fault sealing. So that's what I would say about that. Yeah.
All right, thank you very much. Mr. Murray, do you have anything to add to that? I think that was a strict.
I think the main one is that all of this needs calibration. So you have to be really careful taking observations from the North Sea and using them in the Niger Delta.
Exactly.
And the calibration, there's nothing that really gets through there. And I can see there's another the question there is, how do you manage if you don't have the absence of pressure data? How can we validate fault seal integrity with the absence of pressure data? Because we can, well and truly, in that if we have an observed hydrocarbon water contact, we don't necessarily need pressure data for that. So if we can see it from petrophysics or from cuttings, and we can see a hydrocarbon water contact, we can certainly use that. And that's our key point then, is to say, well, where is a hydrocarbon water contact? And how well does that, if we use juxtaposition analysis, does that explain the hydrocarbon water contact? And if it doesn't, then we can Monte Carlo the hydrocarbon buoyancy effect and or the water buoyancy effect to see how well the shale gouge ratio algorithm works. But our experience in general is that juxtaposition explains a large number of the cases.
All right. Thank you, Mr. Murray. And does anyone have questions again?
There was
Another
another one. So
question.
SGR greater than 0.2 means sealing
Okay.
along fault plane, and there could be sand-on-sand juxtaposition without leakages. I guess that's the whole thing. That's from Good Luck. This is the whole thing, is that working out that 0.2, 0.25, 0.4, what that sealing threshold is. Yeah, you really have to get the known hydrocarbon water contacts and go through and check to see that you actually have sealing. And once you've got that, you can start to work out the threshold. Does that help? Or
Yeah,
Yeah.
I think that.
Okay. All right. I think we do not have any other question.
HK sound is still up.
I think AGK has dropped his question in the chat box.
Okay. Yeah.
Yeah. So
Okay.
on this note, I would like to ask Olaiton if he has any closing address or remark for this session.
Okay. Thank you. Thank you, Wura. Thank you everyone for joining. And I believe that just these few minutes that we've spent together, we've been able to, unravel a lot of things with respect to faulty analysis and appraisal and development, from Prosper taking us back to volumetrics, right? And also be looking at fault evaluation together. So I believe that we have done a lot of things together, and we have been able to answer people's questions and also meet up to expectations, because one thing that we added in the registration is for you to drop your expectations and also to ask your questions in advance. And we got expectations like people want to gain insight on fault analysis workflow, and that was why we did the first stage of the fault polygon evaluation. Someone says they want to be more enlightened about the concepts about faults in the oil and gas industry. I believe I've been able to do that for you. And people were excited, or said they're excited to learn about fault analysis with real-time feed development plan illustrations. So thank you very much for joining, and thank you, Mr. Murray, for taking your time. Wura, over
Yes.
to you.
Thank you very much, Olaito. I'm sorry. I think I saw somebody's hand up. Okay, so I think the question is already in the chat box. Can we quickly take this before we go? So the person is asking Henry Anunandu, sorry, I'm so sorry. What are the key principles of fossil analysis and how does it contribute to increasing reserves? Okay, maybe Prosper can quickly take that, and if Mr. Murray has any other addition, then we can wrap this up. Prosper, over to you.
Okay. So, key principles. So what I would say is that so when we have to consider key parameters. Seems like there's an echo. Okay. So so when you look at key parameters utilizing fossil, for example, I would take a. Can you hear me? Can everyone hear me? Okay. Okay.
Yes.
So yeah, thank you. I'll take a quote from Alan 1989. Alan said something. He said that a fault is neither a conduit nor a seal until we're able to establish what stratigraphic units occur on either side of the fault, and then we'll be able to understand if it's either a seal or a conduit. So one key thing or key parameter to consider is your stratigraphy, or is your stratigraphy. And with your stratigraphy, again, we are not just looking at what is juxtaposed on either side of the fault, which is important, like we've shown in some of the scenarios that we looked at, sand to sand, sand to shale, all of that. But we are also peculiar about top seals, right? So you also need what's it called? Appropriate top seal thickness for whatever reservoir of interest that you're looking at, because you do not want or you want a greater degree of confidence in terms of um, vertical sealing. Okay, you don't want a case where you have worries regarding vertical migration of hydrocarbon. Okay, so we look at top seals, right? We look at the stratigraphic units juxtaposed on either side of the fault. We also look at the faults themselves, fault geometry, fault architecture, looking at the fault throws, fault heaves. We talked about making our faults or putting our faults on a diet. And we saw how when we put our faults on a diet, right, we have a greater, a larger area for our hydrocarbon pool, which then translates or greatly affects our volumetrics and our reserves calculations, right? So we need to ensure that our faults are geologically consistent in terms of throws, in terms of the heave, ensuring our faults in terms of normal, when we're looking at normal faults, normal faults have 65 degrees deep angles, um, and just ensuring that they're geologically consistent, right? So when you do that, you see that from what we've shown today, that it has huge impact on volumetrics, right? And with your stratigraphy, looking at when we looked at leak points and fluid contacts, looking at the various scenarios, when you have certain juxtaposition scenarios, permeable, impermeable, permeable, permeable, that too can determine what fluid contacts you will get in your reservoirs and what hydrocarbon column height that your faults will support or you are able to get from your reservoir. So again, the faults themselves are important for parameters. Your stratigraphy, another important one, looking at your top seals and what is juxtaposed, as well as in some cases SGR within the fault zone, and all of that helps in understanding what reserves you'll be able to get. I don't know if that helps, Henry, or
Uh,
If Mr. Murray wants to add anything, or Lighter.
um, okay, I think there is a follow-up question from Henry. So maybe Mr. Murray can just take everything all together. So he's asking, how do you quantify fossil capacity? Are there industry standard methods or models? And okay, let me take this second question so that Mr. Murray can address them together. So this person, Tolu, is asking, how do you integrate in situ stress condition to evaluate fault integrity?
Okay, cool. Well, look, in terms of the fault seal capacity industry standard methods, there are a set of algorithms out there that have been published, but we found there's been really big divergence from those. And the industry standard for fault seal capacity is juxtaposition then backed with shale gouge ratio. And and really any area we have to calibrate the shale gouge ratio. It's super important to calibrate that shale gouge ratio and show that you actually have a sensible shale gouge ratio for your area. And you can't just take what somebody else has published and then apply it in your area. The calibration is important. In terms of the second one, and it sort of lies into the first one, how do you integrate these in situ stress conditions to evaluate fault integrity? I guess I've published with colleagues on both of these. We've used examples from northwestern Australia in the Timor Sea, which is thought to be an area where stress has an impact on fault seal. And we've shown that really juxtaposition is the key impact here. There are a set of fields there where with the collision of Australia and Timor, it was thought that stress was an issue. And we've really shown that actually a better quantification of what the top seal is the most important bit. So Alan, which Prosper was referencing, he said, well, look, it's all about what's juxtaposed across the fault. And what we've found is that in many areas, there are thief zones or those zones in the top seal that limit the field size accumulation. And unfortunately, those thief zones within the top seal have been confused with in situ stress issues. The one in particular is there a set of seals with limestones in them. And often what happens is as you drill through the top seal, you hit this and they have drilling issues. And it's thought to be, we've got a problem with drilling issues, but fundamentally it's going from a shale to a limestone and then back into a shale. And that's what's set people thinking, well, this is all to do with stress. Whereas actually when we generate the Allen maps and look at where those limestones juxtapose the main reservoir, we find they're the key control on the fluid contact. So the model that we're pushing, that we're proposing to people is this is all about working out the basic geology, in particular the top seal geometry and validity, and then start to integrate it with proper decent mapping before we start to use complicated algorithms that may or may not have utility. So just doing the basics right before you worry about shale gouge ratio, and just doing the basics right before you worry about stress is where we highly recommend that people follow. Does that answer it?
All right. Yeah, thank you very much. Olaiton, you can quickly add your own contribution to the question.
Okay, so I think my contribution basically would be for the first one, Henry, that asked about the quantification of fourth seal capacity. I know when I saw his question, I'm like, is this guy an engineer? Because engineer love they love numbers and figures. So okay, so the idea is that at Avex Solutions, when we do a fault analysis project, we provide you with the probability of the fault, like to trap a column. So we give you like range of figures between the P10 to P19, and we also provide the column height, like that tells you how much hydrocarbon that you have in the reservoirs. And then in terms of the industry standard methods or models, just basically what Mr. Murray and Prosper had said. So the juxtaposition mechanism, the SGL, I think they are the two major mechanisms that people tend to use in the industry for fault seal analysis. So that's just my addition. Thank you, Laura.
All right, thank you, Olaiton. We've come to the end of today's section. Thank you, everyone, for joining us today. And as we wrap up this webinar, I would like to express our sincere appreciation for your participation and for the insightful questions. We hope you found this session informative and valuable. And a special thank you to our speakers, Olaiton Prosper and Mr. Murray, for sharing their knowledge, and to all who engaged during the question and answer session. We thank you very much. Please stay tuned for follow-up emails with additional resources and information on our upcoming webinars. And also someone asked for the YouTube link. It has been shared in the chat box, but maybe they will reshare it again so that people that joined later can have access to it. On this note, I would like to say have a great day, and we look forward to connecting with you again soon. Goodbye and take care. Thank you.
All right. Thank you. Thank you, Mr. Murray. Thank you, everyone.
Thank you.
All right. So
Thank you.
Thank you, Lighton.
Thanks, Guy.
Thank you,
yeah,
Prosper.
can we have the YouTube link again so that people can also just follow up the page until we drop the section recording? I'm going to be resharing. I think I'll reshare this. Yeah. Thank you very much. All right. Bye, everyone.
All right, bye.
Bye. Thank you.
Bye.
Bye.